Hi everyone, I am Navyashri AJ from Siddhartha Central School, studying in class 10H. Today, we are going to discuss a few topics related to our second chapter of physics, Human Eye and the Colorful World. The topics to be covered today are dispersion of white light through a glass prism, Newton's experiment in a glass prism, formation of rainbow, atmospheric refraction, twinkling effect of stars, advanced sunrise and delayed sunset. Let us move to our very first topic, dispersion of white light. Dispersion is very familiar phenomenon to us. It is a process in which when white light is passed through a glass prism, splits into 7 bands of colors. These 7 bands of colors are known as the spectrum of white light. And we also see that these 7 colors occurs in a specific order or sequence. The acronym VIBGYOR helps us to remember the specific order or sequence in which these colors occur. VIBGYOR stands for violet, indigo, blue, green, yellow, orange and red. Though these colors don't appear to be distinct, but we know that these colors occur separately. But why this happens? This is because each of these colors are different in wavelength and bends in different angles. The colors with more wavelength bends the less. The colors which has less wavelength bends the more. That is why we are able to see red at the top and violet at the bottom. Red is having more wavelength, thus bends less. Violet is having less wavelength, thus bends more. Now let us see the Newton's experiment in a glass prism. Isaac Newton was the first to use a glass prism to obtain spectrum of light or the 7 band of colors. He passed the white light through a glass prism and observed that it split it into 7 bands of colors. And also he used another prism to divide these colors or to obtain more colors from it. But this didn't give a result. He then used a prism in the inverted position with respect to the first prism. This gave a different result, that is, the 7 bands of colors which emerged from the first prism rejoined again and emerged as white light from the second prism, which concluded that white light is made up of 7 bands of colors, that is, violet, indigo, blue, green, yellow, orange and red. Now let us look at a natural phenomena or the formation of rainbow. Formation of rainbow is a phenomena which is related with the 3 phenomena of light: dispersion, reflection and refraction. Dispersion is the process in which white light when passed through a glass prism splits into 7 bands of colors. Reflection, as we have learned earlier, is the bouncing back of light when it hits an obstacle in its path. Refraction is the change in direction of propagation of light when it travels through different media. So how these 3 processes contribute in the formation of rainbow? Let us see. Usually we observe a rainbow after a rain or when it is sunny and cloudy. And we can see the rainbow whenever we stand in such a position that our back faces the sun. This is because the sunlight should reach the raindrops present in the atmosphere to get dispersed into 7 bands of colors. Here, the rain droplets are acting as a glass prism. Let us look this process in detail. The sunlight first refracts to the interior of the raindrop because it is traveling through different media, that is from air to water or from a rarer to denser medium. After the refraction, it also disperses into 7 different colors, and on hitting the internal surface of the raindrop, it reflects back. Some amount of light is also refracted, but the colors or the light which falls on the smooth surface of the raindrop gets reflected, and this is known as internal reflection because this is happening inside the raindrop. After internal reflection, it again refracts to the atmosphere and splits into 7 bands of colors. As we have learned earlier, colors with more wavelength bends the less, that are the colors like red. The colors with less wavelength bends the more, like the colors like violet. That is why we are able to see red at the top and violet at the bottom. Now, let us look at another phenomena, atmospheric refraction. Refraction, we know it is a change in propagation or the change in direction of propagation of light when it travels through different media. Atmospheric refraction is simply the refraction of light source entering the different layers of atmosphere. We know that the atmosphere has different layers and these are not stationary. These are also different in its composition and densities. As we come down to the Earth's surface, the layer will be having more density. That is, the layer which is closer to the Earth will be denser compared to the layer which is away from the Earth. So any light source which enters the atmospheric layers will be continuously refracting from a rarer to a denser medium. Let us look a phenomenon related to this, that is the twinkling effect of stars. Do stars really twinkle? Stars are too far away from the Earth's surface. Thus, the source of light from the stars will be only of a point-sized source of light. When this source of light enters the atmosphere, it undergoes refraction and slightly bends. And if we look through these bended rays, we can see only the apparent position of the star, which is slightly above its original position. This is not only the reason for its twinkling effect. We know that atmosphere has different layers, which is different in its composition, like pollution, dust particles, and refractive index. So it will be bending in different directions. So the very next moment, the star will be changing its position, which will result in the twinkling effect of stars. Sometimes we also observe that the stars appear to be brighter and sometimes it is dull. This is because, suppose 5 rays are coming from the stars. Due to the refraction of light rays, 2 of the rays will be refracting or bending into different directions, thus only 3 rays reaches our eye, which makes the star little dull. Suppose 4 rays are refracted in different direction and only 1 ray reaches our eye, which makes the star more dull. This is why we are able to see sometimes the stars brighter or even dull. So now we know why stars show a twinkling effect as a result of atmospheric refraction. Now let us move to our next question. Why planets don't twinkle? Stars are outside the atmosphere, so the light source from the stars should enter the atmosphere and should undergo atmospheric refraction. Even planets are also outside the Earth's atmosphere. So let us assume the smaller circle as a star and the bigger circle as a planet. As planets are much closer to the Earth compared to the stars, the light source from the planets will be much larger than it. To make this point more clear, let us assume the planets to be the collection of so many such point-sized sources of light like that of a star. So each of these point-sized sources will be emitting its own light, right? And on entering the atmospheric layers of Earth, it will undergo refraction. And also it will bend to different directions, and this results in the twinkling effect of each of these points. So here we are also able to see that while some of the point-sized sources are dim, the others are bright. This we had learned earlier. This is because the different rays bend in different directions, showing as a different result. That is, they may appear brighter or even dull. So let us zoom out to look what will be the result of this total refraction. Here now we can see that the star is now also twinkling, but the planet is not. This is because the average variation in the amount of refraction from all these point-sized sources of light will be 0. That is giving us a 0 effect. Now let us zoom in to look. Now we can see that each of these point-sized sources or the light from these point-sized sources are refracting, but it's not giving us a twinkling effect. This is because the average variation in the total refraction of all these point-sized sources of light will be nullified, or the average will be 0, giving us no result. So hope you are clear with this point. Now let us move to our next topic, advanced sunrise and delayed sunset. We are able to see the sun 2 minutes before the actual sunrise and 2 minutes after the sunset. This is also a case of atmospheric refraction. That is, before the sunrise, when the sun is below the horizon, the sunlight is entering into the atmosphere and undergoes refraction, and thus the bended sunlight reaches our eye. So if we look through the bended rays of light from the sun, we'll be able to see an apparent position of the sun which is slightly above its original position, that is above the horizon. So we'll get an apparent position of the sun, and this results in this advanced sunrise. Similarly, at the sunset, after the sunset, the light from the sun will be refracting when entering into the atmospheric layers, right? So if we look through these bended rays, we'll be able to see the apparent position of the sun above the horizon. That is why we are able to see the sun 2 minutes after the actual sunset. To understand these topics more clearly, we should visualize it in our mind several times. So hope you are clear with these topics. Thank you.